Hi everyone, thanks for joining in on a Saturday morning. I can imagine how tough it could be, right? So really appreciate it. I think I'll rather walk, yeah. So we'll start with a brief introduction and then we'll go into the depths of it. So I'm Romil. I have a total of 11 years of experience into data science machine learning. Prior to that, I was a computer science engineer from IIT Indore. IIT Indore, in fact, started with our batch. So I was one of the students in the first batch. I had absolutely no seniors. That was fun. I did see the campus building up from scratch. So it's always great to come to an established IT and see all the facilities around, right? Something that we actually missed. When I go back to the IT Indore after 10 years, it sort of resembles to what this is, but quite not with the grandeur that it operates. Right, so yeah, that's where I started. I got into data science mostly as an accident. I wanted to be a software engineer, and that particular project which I was pulled for needed a bit of machine learning. And this was mostly 2012-13. It was an age where Python packages weren't as famous, right? So if you had to maybe code a neural network, you had to start reading a book. There was no blog, there was no analytics vidya, there was absolutely nothing to help you, no packages either, right? So you had to start from scratch, code through the lengths and breadths of it. And I still remember I took almost 8 months to build a first neural network out of VBM in an Excel, right? Just because the client wanted it, not exactly required it. That sort of opened to me the possibilities that machine learning could actually do. I quickly moved on from there to credit underwriting. So that's one space where you use machine learning to basically approve or reject customer loans, right? So I'm not sure if any one of you have applied for a loan. Show of hands. None. Not even student loans. Perfect. Anyways, so in case you've seen your parents do that, right? There was a time around 2010 where a human being used to approve or reject a customer loan, right? An underwriter used to go through the application. It took at least 2 to 3 weeks. It was a painful process. Around 2012 was when these companies wanted to use machine learning to replace the human-based underwriting process. For the first time, they wanted a machine learning scorecard to basically approve or reject a customer loan real time. I was again fortunate. I got the chance to develop the first of its machine learning scorecard across 8 companies in India, starting with L&T Financial Services. Then you moved on to Axis, Edelweiss, HDFC, Tata Capital, Aditya Birla. Phenomenal success. But the first project, right, I still remember losing my sleep, because if you think about it, right, you're basically running the code. You are rejecting approving customer loan based on a machine learning scorecard. If some customer defaults by some chance, the CUs literally call me in the middle of the day, middle of the night, asking why did the machine learning scorecard approve this customer? Even a second standard student would have rejected it, right? So it was difficult for me to convince them, saying a machine learning scorecard works well on an aggregate. That is, if you distribute or disburse 100 loans, maybe a scorecard would do better than humans for 90, right? But it could always be those extreme false positives, false negatives, both. So that was a very high risk, high stress job that I did start with, but it was a phenomenal success again, right? Within 6 months, we did beat humans with 30 years of experience into that field, right? On an overall, we managed to reduce the default rate from 7.6 to, I guess, 5.2. That was just the first year of this going in. More importantly, we were able to scale to new locations fast. Now think about it in terms of doing it without data science, right? Let's say you're in Chennai, you had to go to maybe Kozhikode, right? So you had to hire an underwriting team from scratch, a team which could knew the local nuances, like the local people, the local businesses, their ways of underwriting, their ways of approving, rejecting. That itself took 6 to 8 months. Then they had to sort of train them on their own systems. At times, few underwriters would go overboard. Some didn't take it seriously enough. We managed to crux that or dilute that entire period from maybe an year and a half to 15 days. 15 days, it all is all that it took to a machine learning scorecard to go live to a new location. Secondly, let's say you're looking into a recession, right? Like the US is right now. So CEO wants to just make the loan approval process a little strict, right? So a central narrative comes in saying stop or make the processes rigid by 10%. Now imagine how could you explain this to a team of thousands of underwriters. Some people might not really take it seriously. right? That 10% could slightly be a percent or 2% here and there. Some people might go overboard, right? They would completely stop dispersing. So it's very difficult when there's a team of maybe thousands of people carrying out such important decisions to control them sitting in a central chair. But now we have a machine learning scorecard. We know the cutoff, right? I know if I move the cutoff from 670 to 675, I would end up dispersing 5% less, right? And my job is done. So the power of machine learning, right, was visible for me for the first time then, where this project went through, and we scaled to 7 different banks, as I said, right, in a space of 6 to 7 years. And nowhere did the machine learning scorecard fare poorer than a human being, right? It was able to be the best of underwriters all the time. Lots of reasons, but something that does come to mind is recency bias, right? Humans, right, we think a lot about what happened in the last week, last 2 week, last month maybe. We tend to bias our decisions based on the recency that has happened. The machine learning scorecard doesn't, right? It's able to be very objective, and it's able to look at multiple dimensions parallelly. I'll take another example to maybe stress a bit on this. Let's say you know that higher the age was the customer, right? You know that. You also know that higher the income, better the customer, right? So let me give you 2 examples. One customer age 25, income maybe 50K. Other customer age 30, income 70K, right? So the second customer is better on one parameter, not so good on the second parameter, right? But you do not know how much of age will compensate how much of income, right? Will +2 of age compensate -10K of income, +3 of age -40 of income? And these are just 2 parameters. Imagine how a human being would make decision with tens of parameters. Directionally, they know what is right, but when it all comes together, right, it's very difficult for them to figure out how those 10 combinations come together to rank 2 customers differently. Whereas a machine learning scorecard can do that quite easily, thanks to the weights, thanks to the betas that are learned through regression. And yeah, basically that's why I thought it worked phenomenally well. That was crucial for me, because in that phase I still wanted to be a software engineer. But looking at this success, I thought, yeah, probably it's easier being a machine learning scientist, right? People need it, and apparently humans aren't as intelligent as a machine could be, in some cases at least. Right, so yeah, that was my 6-7 years. Extremely stressful. As I said, a CEO would still call me in the middle of a night and ask me why did my scorecard approve this customer. I didn't want that. Right, was just too much after a point of time. So I thought I'll take a switch to a slightly easier domain, which was marketing. I made my switch in marketing after 7 years. That was fun because of 2 things. One, you could easily go wrong. Right? How many of you have gotten a call for a credit card in the last week? All of you are right. That was because of some machine learning scientist sitting somewhere not doing his or her work, right? That was you were the false positive. But to be honest, it wasn't much of an inconvenience, right? At least we think it isn't. I know it would be. Sorry for that. But from the company's point of view, it's a very small cost, right? Even if they get it wrong. 1 call, 1 SMS, very small cost. So in the marketing space, you can go wrong without really penalizing the bottom line a lot. And that gave a data scientist a lot of leeway. So I absolutely loved my work there. I made a lot of mistakes, explored a lot of black box models. That was when my research into deep learning actually started. I went on to sequential models. I started a bit of transformers. All the fun I had was on the marketing side, simply because I could go wrong and there wasn't a lot of cost associated with that. After that, I moved to PayPal. I've been here for the last 2 years. Amazing team. I have to say that because my manager's here. Just kidding. Amazing team. Great organization. Right. I've been working primarily into the payments part of the customer life cycle. So anything and everything after a customer clicks on pay comes to our team. Right. We could go into a few use cases. We'll have that at the end of the slide. But yeah, sorry for taking a lot of time. That's been my journey for a decade, and I'll probably hand it over to Kavi to talk about his.
Yeah, hi everyone. I'm Kavikumaran. So Kavi, basically. So I have close to 6 years of work experience in the field of data, I would say, because I started as a software engineer. I was working with data in some capacity, but not a ML scientist when I started. So my role when I started with Wolters Kluwer, I'm not sure if any one of you have heard about it. Wolters Kluwer. One way. Thank you so much. I mean, I've never seen anyone heard about that. Even the folks who are working in that Ramanujan IT park, they call it Voltas. I will feel like I'm a AC repair person or something. Thanks for that. So the thing is, right, that's an enterprise legal company, and at that time, machine learning was not a huge buzz, and not even data science. The maximum that you could hear about was analytics or reporting, dashboarding, not more than that. So I was in a role which required reporting object creation for business intelligence, nothing more than that. So then in 2018, like I started to get acquainted to this term predictive analytics to start with, and I just developed this curiosity of is it really possible for us to predict based on the historical data? So I just did a lot of online courses like anyone else would do. There were a lot of ads coming. Like I think some machine learning engineer got me saying that this guy is really interested in online courses, and I did like 2 to 3 courses, all online courses. Definitely wouldn't want to mention the names, but yeah, it kind of helped me to develop knowledge a little bit. But I wasn't able to get a job with that knowledge because the interviews were really hard. So it was a long journey before I moved to a proper analytics role. I decided in 2018 that I wanted to move to a proper data science role, but it kind of happened by the end of 2019 only. I really had to try hard, and every single day I had to learn new things and fail in a lot of interviews basically before I started my proper analytics career at Bridge I2I. So I was basically deployed at client location right from day one in IDFC First Bank, Mumbai. So life was very different at a bank. I mean, starting from the dress code and the culture, and Mumbai, you know, right? It's super fast. Everybody will be walking fast from here and there. I don't know what work they would be doing. So I was there for a brief period before I moved to Uber because Mumbai was too fast to me. So I moved to Uber, Hyderabad. There I had a good time, and yeah, I think proper machine learning work for me started at Uber, I would say, where we started to work on more sophisticated problems like predictive analytics. Like why I'm saying is, even if you want to pursue the path of machine learning, right, it's not possible that you would end up developing a model right from day one once you get a job. That is not guaranteed unless or until you are so lucky. You might start with something very simple as reporting, automation, dashboarding, and providing some insights. But you just have to keep trying. And Uber was a breakthrough for me. I was there like for around a year, and Chennai called for me, so I came back to Chennai. I was like I was actively looking for a role here, and I joined the pricing team actually. Before I was with payments, I joined the pricing and FX. And guess what? I was with ML teams in Uber, but when I reached PayPal, I again had to do analytics work. So not much machine learning scope. It was a new team basically. So it was a new challenge. You just have to set things up from base. Basically, you just have to start things. I spent like around a year and a half in that team before I moved to payments team. So it has been like 6 months now since I joined payments team, and yeah, of course I moved with an upgrade to the payments team, which my manager was so aware. I mean, so surprised to see someone getting promoted within a span of 1.5 years, right? We were having this discussion when we just came in. So she didn't know that until this point. So yeah, that has been my journey. It could be similar to most of anyone's journey who has joined, who's been a part of data science, right? Or machine learning. If someone is saying that they are having 20 plus years of developing neural networks and machine learning, they might be lying. It's not possible. I mean, a lot of things are coming into light and becoming popular only, and even common people who aren't much into computer science as well, right? They are starting to get interest into machine learning with the advent of ChatGPT, basically. I mean, these days I rewrite my email. I didn't prepare this presentation using ChatGPT because it has mostly pictures and charts, not much content. But I would say ChatGPT is really a handy utility, nothing more than that, in my opinion. But people have started to use it, and now the interest for AI has become a lot more now. So Yeah, I mean, forgot to say good morning and thanks for turning up in such large numbers today. I hope we keep you as engaged as possible, and I want this to be as interactive as possible. So I'll be asking very basic questions in the in the middle. I am expecting some answers from you guys. So before we start, if we move to the previous slide, right? If you had look at that poster that Sham has read, it had a very large title: feature activation, its impact on convergence, and even I don't remember the entire title. But it sounds very complicated. But honestly, it's a very simple concept. I would say it's an idea. It's not something that's already available over there in the internet. So you can feel free to Google feature activations or even ask ChatGPT what feature activation is. It will give you a very good answer because I tried doing that, but that is not feature activation. Basically, it was an idea that my good friend here, Romil, came up with. So we are so excited to present in front of you an idea that is not something that you can learn from the internet. It has not become that popular yet, but we have tried a few things on a neural network, and it had worked so well so far. So we wanted to present you that idea, and this, in my opinion, is more like a discussion, and we are looking forward to your feedback, thoughts, comments, everything. So you need not consider this as a proper workshop. Rather, it's more of a brainstorming for us. Okay. Just I have a couple of questions. How many of you have a proper programming background here? Any language? Okay, it's 50, right? Okay. And how many of you have a decent idea about machine learning basics? Okay. Then I think we might have to go through that first part very quickly. Deep learning? Lesson number. Thank God I prepared the slides for you guys. For those who didn't raise their hands, thank you so much. So we'll start. But before we move on to the slide, I just want to ask a very basic question. So for someone who might have tried any aptitude question, right? Even be it as a part of your entrance exam or be it as a part of your whatever interview process or anything, you might have seen a question like fill in the series or guess the next number in the series, right? So I'll give you a series, very simple series. Pardon me, that question is very simple. Let me know what would be the next number. So if there is a series of 2, 4, 8, 16, what would be the next number? Why aren't you guys loud? You gave the right answer. You can be a little louder. It's how come? I mean, that's the right answer. How come you were able to say it's 32? What made you say that? So 2 power, yeah, it's a 2 power x basically, right? It's a function. So you are able to predict, in this case, you kind of did a prediction. You are able to arrive at what would be the next number because you are able to approximate it to a function, right? Here in this case, it's 2 power x. Consider this example now. You have an input, set of inputs, and we don't know what the function is. And then we have an output there as well. Take any guess what would be, do you think these numbers are random or is there any relationship when you look at it at a high level? Do you think so? These look random, right? Not, at least not simple. Okay, I will give you a clue now. What do you say now? What would be the other number? Any guess? Okay, that's right. Now, it's easy for you to figure out what f of x is, right? I mean, I honestly didn't know the actual formula without referring to Google, but I'm guessing any one of you might know. Okay. Same. Okay. So, in programming terms, if I were to give you a task of converting Celsius to Fahrenheit, how would you write? So, here's a basic Python code that could accomplish a task, the same task. So, this is traditional programming. So, if you look at these three parts, right, there is an input, there is a black box earlier, which seems to be a function y equal to c into 1.8 plus 32. That's the function. And then we have the output Fahrenheit, right? In traditional programming, you will know the input, you will know the function. All you have to do is come up with the output. So you just have to define a function, pass in a parameter. For those of you, if you don't understand what a parameter is, feel free to raise your hand. I just have to give a value of x. So in this case, if I give a value of 15, that 15 will be multiplied with 1.8 and a 32 would be added, which will give me the output. So in machine learning, what is different? Basically, in case of machine learning, you will be having an input, you will be having an output, but you won't know the relationship. So in this scenario, when I didn't give you that clue of whether it's a Celsius value, you are clueless, right? What could be the number? What could be the relationship? Machine learning is all about finding that relationship. What is the best possible equation? It need not be an equation all the time, but you just have to find the relationship. What kind of relationship exists between the input and output? And it need not be simple all the time. Here it's a very simple linear equation, I would say. But in reality, you might be having a lot of inputs and you might have to do the equation can be a lot more complex, and sometimes it might not match with the exact output. There will always be some error with the predictions. So that exactly is what machine learning does. So in traditional programming, you have the input, you have the function, you just have to write the code to get the output. But in machine learning, you have the input, you have the output, and again, take it with a pinch of salt, because inside machine learning, there are different types: supervised, unsupervised, and all those things. I'm talking about supervised here. Of course, you won't have the output for unsupervised problems. So you have the input, output, and you just have to figure out a function that generalizes well, or that helps you map the input and output. That's a very high level understanding or overview of what machine learning is. Any questions thus far? Is this clear so far? Right. Okay. So what is deep learning then? Yeah, there is a definition mentioned. It's a quite straightforward statement that says it's a subset of machine learning that has a lot of layers. Have you ever seen a neural network architecture anywhere by any chance in a Google search or anywhere? How many of you have never seen a neural network architecture? You will be seeing one pretty soon. Okay. So yeah, neural network architecture, it's super intimidating. It's super scary when you look at it, right? You'll be having a lot of nodes connected. There will be connections all around those nodes and all those things. So learning deep learning, I would say, is not as easy as learning machine learning. At least until this point, you would have to refer to a lot of sources from different platforms and different blogs to learn deep learning. And is it really worth it to learn deep learning, or is it really that powerful? So let us have a comparison on how deep learning is different, or how deep learning provides an edge over machine learning. So this is the picture. This is one of the picture I took from Google. And the moment when I learned deep learning the first time, the moment I had a look at this particular image, I thought, let us skip deep learning and stay with machine learning only. So that's how intimidating it is. There is a lot of inputs, and how can I even make sense of what happens inside all of those nodes or the connections? They pretty much connect everything, right? So that is when things get little complicated with deep learning. But as it shows, right, the more complex it looks, it definitely provides you with more power in terms of accuracy or performance, and at the same time, the variety of use cases it serves, right? It's really awesome. So for any unstructured data, if you were to work with audio, video, or even text data, the ChatGPT model, all of these are deep learning models basically. So that is one of the reason. And from a data scientist standpoint, if you were to develop a deep learning model, what's the biggest advantage of deep learning is that the feature engineering effort. Okay, let me quickly do a recap on what a feature is. In my previous example, Celsius was the feature, Fahrenheit was the target variable, and the function, whatever that y equals, was my algorithm. So feature is simply the input. Now what we mean by feature engineering is, if you were to develop a machine learning model, you would have to extract information from the raw data you have. Let us take a very simple example. Let us say you have a date column. Now, the date column as such might not provide you any insight because the algorithm will not be able to extract information. But if you were to extract the day, or what day of the week it is, or the month and the year part, if you can extract these individual pieces and put it together as different columns or different features in this scenario, then the model would be able to make sense out of it. So this effort has to be put manually. You just have to put in this effort, and only then machine learning can do a better job. But in case of deep learning, and of course, feature engineering requires a lot of domain expertise. One has to know the data so that they can extract information out of it. But in case of deep learning, that's really not the case, where you just have to pass on the data in the first node. The x1 to x6 is the input nodes, where you just have to give the data, and the complex web-like structure that you see here, that takes care of all the feature engineering, at least most of it, so that you would end up with the output. So it's easy, right? From a data scientist standpoint, it makes things a lot easier. But yeah, I'll explain you the individual components or the mechanics behind deep learning in the next slide. But that is one of the reason we use deep learning. For instance, if there is a picture of a bike, feature extraction algorithm inside of deep learning splits it, or it helps you identify edges, rounds, colors, or whatnot internally. You just don't have to explicitly mention those to the model. It is able to do that internally. And of course, the other 2 points are the complexity and the scalability it offers, and its performance on unstructured data. So this is why deep learning is important. It definitely provides you an edge over machine learning for few scenarios. I wouldn't say for all scenarios, but for a few scenarios. Questions? Any questions so far? No questions? Yes, that will be handled in the hands-on session. So I think we skipped the agenda slide, but let me quickly give you an agenda. So I'll be walking you through the basics of deep learning, how things work. I'll be helping you understand the different components, the terminologies, and in the later part where Romil will be walking you through the exact idea, the proposal that we had, and then post that there is a hands-on session where every single thing that I'm describing here would be coded, and you will see the input and output. You will see the difference. You will observe the difference. But it's not an image processing problem that we have here. But yeah, just to set the expectations. Okay, let us try to understand that big diagram. Let us try to split it into small parts and try to figure out what a neural network actually is. So let us consider one perceptron, meaning one single circle that you had. So for a single perceptron, there is an input, there is a weight, there is a sum, activation function, and output. This is the flow. For any perceptron, this is the flow that would happen. This is the set of operations that would happen inside a perceptron. So x1 here in this scenario, if you consider the same Celsius to Fahrenheit example, x1 here means, yes, column name, the name of the column we used, Celsius. Yeah, right. So x1 is the Celsius, and what happens is there's a weight associated with it, which is nothing but in our scenario, the equation, right? 1.8, I'm guessing. 1.8 would be the weight. And there will always be another component, which I haven't mentioned here. So in different architectures, you will see it different in different places. So there is an x0, which you might see to the top of x1, or maybe it might be connected to the sum node from the bottom. But there is an x0 component, or here in this case, I've described it as w0, which is called the bias. I think it's getting too technical. Let me try to explain things in much more detail. So for w0, bias is nothing but a small offset value. Let us say you have a line equation. Assuming the line passes through the origin, right? The number of possibilities you have on that particular line is limited. So if you were to explore the entire space in the graph, you just have to set a different offset, meaning your graph can start from y equals to 1 in the x-axis. So that offset enables you to explore the space, explore different possibilities inside that graph. And it basically introduces a little bit of error so that you can explore different possibilities. So here x1 would be the Celsius value, like you had mentioned. W1 is 1.8, and there is a sum. And we will come to the activation function. Here it's a simple, let us assume it's a simple equation, linear equation. And then we have the output, which is the Fahrenheit. So how does the neural network figure out what is the value of W1 and what would be the right function to apply and all those things? But before that, is this equation clear? We just have to add the bias W0 plus x1 into W1, and that would give you the y. And this is the operation of one single neuron. No matter how many neurons you have inside a neural network, the operation is going to be in the same order. There would be a weight associated, and there would be a sum and activation function followed by an output. This will always be there. So if you were to try it out for 3 inputs, this is where the equation looks a little bit scary. But what it does is basically x1 into w1, x2 into w2, x3, xn into wn, plus of course the bias. All of these are summed together, and activation function is applied for an output. A very good example for the first one is again Celsius to Fahrenheit. Probably for 3 inputs, you can think of any scenario that might involve 3 features to predict the output. So any questions? I will explain you each and every component or how the neural networks work from this diagram. But before that, any questions on what x1, w2, sum? I'll come to the activation function very shortly, but any questions till now? How come you guys have no questions? Am I that clear, or is it not? I mean, you are not able to follow anything. Sorry? X cube. Which one? Mm-hmm. No, that's actually a sigmoid curve. Yeah, that's okay. Yeah, he will go into much details. But yeah, until then, please stay awake. Please don't sleep, then I will be blamed. Okay. So let us now try to understand how the model was able to correctly identify what is the right value for W1. Right? In this case, 1.8 was the right value. How did it do that? So it doesn't know for sure when it starts. It starts with a random value. Random weights are being assigned. So let us say in our scenario, it assigns a value of 2. Now, again, the bias is also something that gets updated. If you look at the diagram very closely, right? Ignore the 4 nodes for now. Assume there is just one single node. As you can see, when the model is training, there is a back and forth movement between the input and the function, net input function, or the sum function basically. And there is also a movement from the node that is below the net input function, which is nothing but the bias. These 2 numbers are getting updated. So let us say if W1 is initialized to 2 and the bias is initialized to say 40. Now, if I were to try it out on any example Celsius value like 15, I would be getting a higher Fahrenheit value, right? Now I know that the actual Fahrenheit value was supposed to be like, let us say somewhere around 50, but my output would be like 60 or even more than that. Now I know that my model is not doing well, because at the time of model training, you would be giving both the input and output. The model compares its prediction with the actual output, and it says that, okay, actually my prediction is higher than the actual value. Now it reduces the weight. It reduces the bias. This step goes on. It keeps updating the weight and bias until you come up with the closest possible value. Now this happens actually for a lot of examples. I just showed you 5 examples of Celsius to Fahrenheit. But in reality, when you are training a neural network, it will be on at least thousands or if not millions of samples. So it cannot do well for all samples, but it makes sure that the error that you have, right, it's minimal. And in this case, right, let us say in our case of predicting the Fahrenheit value, how would you quantify error? Any idea? How will you say that? How will you measure error here? Let us say I'm predicting a Fahrenheit value or any number, continuous value. Yeah, the difference, right? That's mean absolute error. So we can do that actual minus predicted, find the absolute value for all the samples that you pass in. Let us say I have 10,000 values. For all those 10,000 values, the error would be measured, a mean would be computed. Now I have to make sure that this particular mean is at the lowest possible for the training data that I have provided. At that point, the model training stops, and that actually leads to the model training and learning and all those things. That is how you actually end up with a function like y equals 1.8 into c plus 32. Now coming to the activation function. So in this case, it's just a simple linear equation. Let us consider another scenario. Let us say, how many of you watch cricket, follow cricket, IPL? Okay, 50% at least, not bad. So let us say, consider the same diagram again. You have 4 features, and let the 4 feature be the number of batsmen, number of all-rounder, the number of bowler, and the number of hours spent by the team in training. Now I want to predict the team's chances of getting into playoffs. Unless it's CSK, it's very tough. I mean, for CSK, you can say it's right away. I'm a CSK fan basically, but sorry to Mumbai fans if you are hurt. But yeah, if I were to predict the chances of a team getting into playoffs, what do you think would be the problem using the current approach so far we have discussed? We have the inputs required. We have the number of batsmen, number of bowlers, and all-rounders. We also have the number of hours spent. But with the current approach discussed so far, you can have a look at the equation as well. There is one problem that won't enable us to predict the output. The output I need is whether or not my team would get into the playoffs. Yes or no type, right? So that's a classification problem. What we are seeing is a linear equation. So regardless of it's just a one node or a series of nodes, or like a node with 4 outputs, we always end up with a linear equation. If you look at it, let us say the model feels like it's a batsman's game. I need more batsmen to get into the playoff. And that scenario, a higher weight would be assigned, an equation would be generated, and there would be an output. But how would that output look like? So if the weights are like, let us say 6, 4, 2, and 1, it would look something like 6 into feature 1, x1, plus 4 into x2, plus 2 into x3, plus x4. Right? This is a continuous value. You will end up getting a continuous value. So how do I make sense out of that? The number might look something like a 300. What does 300 mean? So that is where we need different activation functions, meaning when there is no linearity in your data set, when the outcome that you are expecting is not a linear outcome, there you need different activation functions, and there are quite a few examples. In this case, we need a sigmoid function. So what sigmoid function does is it gives you a value between 0 or 1. It's basically very suitable for binary classification. If you were to try out an yes or no problem, sigmoid function is something that you might want to use. So that is where activation functions come into picture. So here are a few examples of activation functions. So linear activation function, you can use it to predict continuous values. Sigmoid is for binary classification. Tanh is more of a extension of sigmoid that enables your output values between -1, 0, and 1. So he knows everything, right? You keep answering. And thank you so much. You're super engaged. And there is a ReLU function whose values range from 0 and beyond. Either not 1, it can go. No. ReLU function can take values from 0 and it can go beyond 1 as well. And then we have the softmax function, which is ideal for multi-class scenario. Let us say in the same case, right? If I want to predict which position my team might end up in the points table, that's a multi-class problem. There are 10 positions, right? So in those cases, you have to use a softmax. And loss function is something which I just explained, right? You just have to measure what would be the error. In this case, you mentioned that it's mean absolute error. There are different other ways: mean square error, root mean square error. And in case of classification problem, you have loss functions like cross entropy and all those things. So this is at a very high level, the components of neural network. And if you go back to the previous diagram, right? When you define or when you try to understand the way someone can read or explain this neural network is, this is a neural network that has 6 inputs in the input layer, and there are like around 5 hidden layers, and basically the neurons are nothing but the nodes, I would say, and each of the hidden layers perform its own task. So there is an activation function associated with each hidden layer. So basically hidden layer is called hidden because you don't actually get to see what happens in the back end, but there is an activation function. The things that I mentioned, right? Sigmoid, tanh or whatever. There is an activation function associated with each of the hidden layers. So here we have 5 hidden layers, and we might even have 5 different activation functions. And then we have an output. The reason we have 2 outputs in this case could be it's a binary classification problem, right? So this is how you can interpret a neural network really quick. I know this is a very simple explanation because based on the type of the hidden layers, your neural network can be classified as recurrent neural network or convolution neural network, but those are super advanced. But for you to get started or for you to understand this particular session, right, this information should be good enough. Thoughts or any questions? So these terminologies I mentioned, right, hidden layers, nodes, activation functions, every single one of these parameters would be required to complete a neural network. It would be required while you are coding, and you will see it during the hands-on session. Yeah, please. You can call me Kavi. Please don't call me sir. I feel so old. Mhm.
C equals to 1.88 plus 32.
Okay.
Okay, so why we are not taking like 2C equals to 2 into 1.88 plus 2 into 32 or 0.5 C equal to divided by 0.5?
It does. In the back end, it actually does. The model trains different values for C as well as the plus 32, which we call the bias here, right? It tries different values, but when you compare it with the actual output, say, let us say in this scenario, the actual value for 15 would be 15 into 1.8 plus 32. That gives you the actual Fahrenheit value. If I were to try 2 in place of 1.8, that might give me a value of 62, right? 62 is 3 units or 3 points away from the actual value. Now the model will understand, now it will realize, okay, my output is a little
In a
larger.
higher range.
Yeah.
In the, so you can make it like 0.5 also. We can divide it by 0.5 y. Now it's 1, it's multiplied by 1. So we can make it 0.5 y also C into 1.8 by 0.5 plus 32 by 0.5. We can make it in the lower range. Why we are doing it only means like this is the ideal equation I can say for conversion of Celsius to Fahrenheit. Then why we are not making it like means lower range numbers or in the higher range? Why only this particular ideal equation we are taking it?
So if you divide it by 2, right, it will. I think this mic works. So if you divide it by 2, it would be y by 2 is equal to c into 0.9 plus 16. That's the equation.
Yeah.
But in this case, you want to predict y, not y by 2. So if you divide by 2, it will be throughout, on the left as well as the right.
So does it will make any change? I mean, in
You want
the
to predict y. You want to, given this Celsius value, you want to predict the Fahrenheit value, not Fahrenheit by 2 or Fahrenheit by 3 or Fahrenheit by 4.
okay.
Given that y, only this equation can exist.
Y is nothing but it's not an arbitrary value. In this case, we wanted to predict y, like Romil had mentioned. We wanted to understand the Fahrenheit value, right? Why would I want to predict Fahrenheit by 2 all of a sudden?
So we'll get a lower range. I'm saying like suppose I need a range in the suppose if I predict a model for a glucose level. Okay. So like I can make the glucose level range a little bit higher. Okay, like now the doctors are prescribing, suppose is the minimum level range is 80. Okay, 80 to 110 for fasting and all. So like if I want to make it, want to come to a lower range, okay, or to make it to a higher range. So if I want to make a model like that, then with some other features, if I add it, then can I do like that? I mean, I want to say if I change the if I make a model and change the equation like this, okay, by multiplying some means with some scalability, okay, multiplying some numbers. So will it change in the there will be a change in the model or?
So as Kavi mentioned, right, the function is learned by the model. The function is not something that we sort of guess or come at. You have an input, you have an output. If you change the output, given the same input, the function changes.
By bringing down, do you mean you want the values to be lower and hence you cannot lower down the ground truth, right? Just because I want if I want to have a cool climate in Chennai doesn't mean I can update the temperature value to 16. That doesn't change the weather, right? Ground truth remains the same. If you want to have a lower dosage value, It should be the fact. If you want to train a model on a false value, the value that you might want to see in reality, that's different. Then it's bias, I would say. You want to see a value of 16, but the reality is 32. You cannot give model false values just because you want to see values closer to 16 in the predictions as well.
So
Right.
then how will do a future prediction? Means from a particular model, I will do a future prediction.
So you have this
because
equation.
future prediction means like we have to guess something.
So you have
Yes.
this equation, right? You have to plug in the Celsius value and you get the Fahrenheit value.
No, this was a simple example. I didn't mean to give you an equation for every single problem, right? There wouldn't be an equation you might be able to see, and the number of features would be different. Yeah, please go ahead. Yes. Yes. You will have the relationship inside a model. I mean, when you create a model, when you finish training a model, the model would be available in different formats. But of course, you just can use the model object and pass in the inputs that you might want, that you are interested in predicting, and it will give you the output. It's just that you won't be able to see an equation outside. Exactly right. It's a black box. Just for understanding things, I mean, explaining things in a much simpler manner, I took this example. This is not a machine learning use case, of course. We do validate, right? So let us say we have the ground. I mean, if you want to predict the sales for next month, you would have sales numbers for this month. You would have sales numbers for this month last year. You would have a lot of data, right? What you're saying is forecasting, right? That's forecasting. So if you want to figure out what would be the ground truth, you would have to, I would say, wait.
Sir, forecasting can be done from the prior knowledge, no?
Yes.
So if this is the prior knowledge, and if I want to make a forecasting, so I need to change this equation by multiplying or by dividing some constants.
But why do you want to change the equation?
So let's say you're training a model, the same example, Celsius and Fahrenheit. Let's say you're training this model for 2022. You have trained this model, you have the ground truth data from Jan 2022 to December 2022. So your model is trained, you have validated with ground truth, you have validated the error, MAPE score, the mean absolute error. Now you know this is the equation, right? Now you take that equation, you don't need the ground truth now. You have validated, you know that this is my equation, it is 1.8 plus 32, right? Now you take this. For Jan 2023, I have all my input features. Let's say Celsius is one of my input feature. I take that feature, I multiply that by 1.8 plus 32, and that is my output. I don't need ground truth for the next year. Unless there is any events like COVID, where your features itself will change, where your ground truth is no more valid, right? Because it's COVID, people start shopping online a lot more. So that point in time, you need to introduce new features like, hey, there is an uplift due to COVID, right? Then you retrain the model with the new data, validate with ground truth, and then the new equation will get updated. As long as those events don't happen, your existing model will still hold good for forecast. Yes. Updating, exactly. Well, even for our use cases, we keep refreshing the model every 6 months to make sure the pattern still holds good. Maybe this 1.8 might not hold good at that time, right? There could be a change. It could become 1.8 to 1.9. So we keep refreshing the model, we keep fine tuning to see if the ground truth still holds good. So that's how we do the forecast.
I mean, yeah. Please go ahead.
Yeah, just a quick question. The feature activations, the title of the workshop, does it relate to the activation functions of a neural network? Does that have a relation?
It's actually an extension on activation functions. You're trying to solve some of the
We'll-
limitations. But we'll come to that
We'll come to that.
Okay.
Yeah.
immediately after
We are
this.
just setting the context so that, I mean, you guys are able to relate when we are trying to explain the other part, right? We're
Yeah,
just setting
yeah.
the base.
Okay,
That's
okay,
it.
thanks.
Yeah.
So in that equation where we are having 1.8, 30 to all these things,
Hmm.
initially it will start with some random numbers, right?
Random weights are
Right?
initialized. Yes.
Then only you are going to accuracy you are going to check. Final point you are going to fix. Right?
Yes. Yes.
Is that correct, my understanding?
Yes. That entire process of doing this iteratively is called gradient descent. That's how neural
yeah,
networks accomplish this process. But yeah, at a high level, this is what happens.
We'll get started with activations.
Yeah, I mean, if there are no more questions, I'll hand it over to Romil for the main part.
Thanks, Kavi, for setting up the context, right? We'll take some more practical nuances of what Kavi discussed, which will help us get a little bit more clarity on what we went through so far, right? So let's take it very easy, one example at a time. I'll take an example which is very close to all of your hearts, something that all of you are actually waiting for, your placements, right? So let me draw a graph, right? So I'll take an example very close to your heart, your placements, right? So let's say I put happiness on the y-axis and your income on the x-axis, right? So I'm assuming most of you wouldn't be earning anything, so income is 0. But I might be wrong. Okay, let's assume it's a very small value, right? But you're still marginally happy, quite happy, decent happy, right? So let's say 4 units of happy right now. Okay. Let's say you have an amazing next 2 years. You get your dream placements. You end up making some 25 lakh. Fair enough. Make a wish. In fact, I'll grant it. 25 lakh, cool, perfect. So let's say you make 25 lakh in a couple of years. It makes you very happy. Let's say your happiness goes to 7 units. Then you work very hard, probably as hard as Kavi, and get a promotion right in the first year, as he talked about.
Mine is not in the graphics on the left hand side.
Let's say your income probably goes to 35 lakhs. Happiness again increases, goes to 8.
Do I look that happy?
Let's say you grind for 10 more years, lots of promotions, become some director, income goes to around 2 crores. Probably happiness goes to 9, right? Then you yeah, let's assume for the sake of this exercise that income brings in happiness. Probably not, yeah. Let's say after that you make your startup, becomes a unicorn, you end up making 1,000 crores a year. Happiness probably 9.5. Let's say at some point of time you beat Elon Musk. I don't know how much he makes. I'll mark it as infinity. Your happiness goes to 9.8. Now you'll see there's a very unique relation right here at the start. Just 25 lakhs were enough to get you an incremental happiness of 3 units. Here, you needed 800 crores to get an incremental happiness of 0.5. And here, probably infinite income to get an incremental happiness of 0.3. Right? So, assuming happiness is related to income, you definitely see it's not linear. Right? At the start, the incremental happiness will be very easy for you to achieve. Very soon, it will become probably difficult, and after a point of time, it will tend to saturate. It will almost become flat. Right? After a point of time, no matter how much money you make, you probably might not be happy. It might also go down. Let's not pray for that.
Depends on individuals, right?
Probably not for
Not for us.
not for Mark Zuckerberg at least. Yeah. So if I go back to the Celsius Fahrenheit example, right? If I take that equation, let me write that down. Celsius is equal to 1.8 into Fahrenheit plus 32. Oh, my bad.
It's hard to memorize.
So in this case, every time Celsius went up by 1, Fahrenheit did go up by 1.8, right? Till the less of eternity. There were no upper limits. So that is what you call a linear relationship. As x increases, y keeps on increasing by the same quantum, which is 1.8 in this case, right? Whereas in the example that we did take, happiness is dependent on income, but not in a linear fashion, right? The beta here is quite high. It decreases, almost becomes 0. So in a sense, the beta that we have is self-evolving. In other words, the relationship that we have between these two variables is not linear, right? Now, if you think about it, most relationships in real life are non-linear. We've taken some examples. Let me go back to the PPT, right? let's start with income and repayment capability, because as I said, I started my career with loans. Generally, with low income, definitely you have a very low repayment capability. As the income goes up, unfortunately, expenses also go up. So your liquidity doesn't really rise in the proportion of your income. Right? If you make probably 1 lakh extra per month, the liquid amount doesn't become 1 lakh extra. Right? You end up increasing your expenses as well. So while as a loan repayment customer, you become better, but not in the proportion of your income. Right? Eventually, after a point of time, your expenses almost sort of catch up and your repayment capability saturates. In fact, we did see in some of our data points that richer customers were tending to have more defaults than the middle class or the poorer ones, right? Because the customers between 30K to 80K tend to live within their means, right? They don't exactly take a loan that they cannot repay, but a customer with more than 10 lakhs per month ends up being more ambitious, right? Ends up taking a lot of debt risk that they probably might not be able to repay. So again, the relationship is not linear. Look at everything that we studied so far. It would tend to assume linear relationship. Let me go back to the equation, right? Yeah, right. It tend to assume linear relationship. It would tend to assume that as x increases, y tends to increase, and by the same amount. Something that might not work with real life example, right? Let me take some more example. So if I had to sort of quantify this relationship, I would say it sort of represents some of a logarithmic relationship, right? With income, repayment capability increases, but in a logarithmic fashion, not linear. Let me take one more example, right? In case Shark Tank fans, anyone? No? Okay, quite a few. Great. Perfect. So I'm not sure if you remember, Piyush Bansal recently made this comment, right? A lot of startups at the start. In fact, let me start with the zero, right? At the very start of a business, we absolutely have no marketing spend, right? But still have some sales. Let's assume that's 20, right? 20 is the sales that you get without any marketing spend. As you start doing more marketing spends, you end up getting more sales. After a point of time, you'd end up reaching every customer that you could ever reach. You could end up influencing every customer that you could ever influence, something that Cred has, right? So many ads. I don't think there's anyone left who is yet to be influenced by Cred. So if you end up spending more on marketing after that, the sales won't increase. It will tend to flatten. Another relationship of a logarithmic nature, right? As Kavi mentioned, this was a sigmoid relationship. It's actually very difficult to have an example, but I've tried to cook something up, right? Might not always reflect with your real life, but yeah, just humor me for the sake of it. An employee in a company that I feel has a sigmoid kind of a relationship. Let me explain why. At the start, when you're very new to a company, there are a lot of hiccups, right? You don't really know who to reach out to. There are a lot of access issues. You are struggling to understand the domain, right? You're struggling to make friends. So your productivity slowly increases, right? As the X here is vintage, your Y is productivity. As you spend more and more time, the productivity increases, but yeah, there's that hiccup, right? It's a slow increase. After a point of time, you get really comfortable. You start finding a lot of low-hanging fruits. You start finding a lot of opportunities. You end up impacting the business. You end up impacting the company. And that's where the S, or the volatile part of the S forms, right? The one marked in blue. I'm not sure if the colors are visible. The one in the between. Sky blue, yeah. Right? That's where an employee, with respect to productivity or incremental productivity, is at its peak. After that time, you see all the low-hanging fruits being actually sort of plucked. You have probably done everything that you had learned so far. So again, the incremental productivity becomes a challenge, right? You tend to saturate. You tend to not have probably a lot of fresh new ideas, and hence the incremental productivity then again tends to saturate. I won't say this is a time to change the company. This is probably a time to upskill, and probably right. That's where HR should intervene and maybe try and get an upskilling program to make sure the other part of this also starts. This relationship is referred to as sigmoid. It's a very, very, I won't say famous, but it's a very commonly used activation function. I guess for another reason why is because most of the relationship in life tend to go through this pattern as well, right? It could be even how love blossoms, right? The way romance grows. I don't know, probably too young a crowd to ask that, but married people, if there are any. No? Okay. No. Would you agree? Thanks. Okay, so where exactly are you in the curve? On the end. Okay, already reached there. Perfect. So you know what to do, right? Hopefully that works, yeah. So we'll go back to one more relationship. Let's look at an exponential relationship. Again, for Shark Tank fans, this is generally how valuation of a successful startup grows. Investors don't really want linear returns. If they would want that, they would rather invest that in stocks or fixed deposits. If someone is investing in a startup, they want exponential returns, right? So any startup which is successful will end up having exponential valuation as the vintage goes. Right? Otherwise, it's shut down. So again, in this case, the relationship of the valuation with the vintage of a startup tends to be exponential. It's not linear. Right. Now let's look at what hidden layers are. Sorry, I know Kavi did ask this before.
I think he was the one who had a question.
Please go on.
No, on the feature activation, right? Understand how this
God, it's different. Perfect. I'll come to that right in this slide. In fact, right after this slide. I'll quickly cover hidden layers and then I'll come to. But yeah, what we are discussing right now is feature activation. It's more of a research on top of the layer activations based on the limitation that we did find. And it does seem to improve the accuracy a lot. We'll see that in one of the use cases as well. Right, so we'll come to that. But before you go to activation, let's quickly look at what hidden layer is and what does it do. So let's say we have 3 features. An easy way to make that model would be to have one beta for each feature. In fact, let me go to the whiteboard again to explain this. Thank you so much. Let's say you're buying a house, okay, in Chennai. You know the price of the house would be a function of the carpet area, right? Let's assume is 100 rupees per square foot. Okay, so this would be a simple equation. Given the carpet area, you'd always know the price of the house. Now let's say you're too lazy to do the hard work, so you find a broker. So every house you pay, let's say you have to pay the broker 500 rupees. So it doesn't matter what the area of the house is. The constant price for you would be whatever the price comes out plus 500 rupees. Right? So this 500 is the bias, something that we refer to as the bias or the intercept. Always look at it as the broker fees because it's constant. It's not exactly dependent on the other parameters of the house. Right? Now let's say you also take a house in a society which applies floor rise. Is that a concept which is common in Chennai? Floor rise. At higher floors, you pay more prices. No?
No, lesser the floor you pay more price.
Is it? Okay.
People don't prefer.
It's more.
Yes.
Okay, I'll change the example. Yeah. Okay, let me get some other parameters. Uh-huh.
It's going to be cheaper, then the price will slightly increase as you move down the ground.
Achha, in Bombay, it's the other way around. You get to
Because
pay
Bombay,
to get the view.
it's too much traffic, people can't see anything
Exactly.
from their windows. So they want to see people.
Exactly, right? So let's say you're in Mumbai, right? So your floor into probably 10 rupees per floor. Okay, let's say this is the basic equation that we have. Given the carpet area, given the floor, we can predict the price of the house. Good so far? Good, right? The intercept always has to be constant. Yeah, so always relate to it as broker's fees, right? No matter what house you take, 500 rupees would go to the broker. Always constant, yeah. Perfect. Great. Okay, let me probably also add number of bedrooms. Maybe 10 into number of bedrooms. Now this equation, oh sorry, my bad. Thank you so much. Right, so this equation in isolation looks good, but you'll see a lot of weird things happening if you just make a decision based on this equation, right? So pay very close attention in the next 5 minutes. Tell me, what does come to your mind when you see a house of 600 square feet? Any reactions? Small house, right? Okay, not too great, not too bad. What comes to your mind when you think of 3 BHK? Amazing. Perfect. Now, what does come to your mind if I say 600 square feet and 3 BHK? Definitely not something that you want, right? So that's when interaction would have a lot more effect compared to isolation. When I said 600 square feet, you're okay. When I said 3 BHK, you are in fact ecstatic. But the combination was a deal breaker for you, right? So this equation will never really capture the combination for you. It only looks at bedroom into 10, carpet area into 100. But what if that combination is simply too weird for you to make a deal? The price would go down. That's where the neural network comes in. If I go back to my slide, that's exactly what we try to do in hidden layers, right? Hidden layer is an interface, is a framework for all the features to interact with each other and create combination or interaction features, right? So let's say if I have 3 features, and let's say I have 3 neurons in the hidden layers, these 3 features come together to form one complicated feature, which is some weight into F1 plus some weight into F2 plus some weight into F3. What are the ideal weights? We'll come to that later. But just think of it as a combined feature which basically takes into account all possible interactions, because in most cases the interactions could have a very different effect compared to features in isolation. There's also a bias. Yeah, there's a bias everywhere. My bad. Perfect. Is the reason for or the inspiration behind hidden layer clear? Exactly. But it can be a different constant. So think of it as if a new feature is being created here, right? This new feature could have a different constant compared to this new feature. And this new feature could have a different constant compared to the previous 2 features. Right.
So what if we add the biases that are, so here you have taken W0, W0, W0,
Mhm.
but if we consider them as B1, B0, B1, B2, because they are different,
Okay.
we just add B1, B2, B3,
Mhm.
and then add not, we just remove it from this equation and rather add it at the end of our process.
The reason that becomes difficult, right? Let me create this equation. So let's say the new features are called, what do I call them? Let's say I call them F11, F12, and F13. Okay, now the net equation that I'll create is y is equal to some weight, maybe beta 1 into F11. Sorry. Now let me break this F11. And this was that complicated equation that came here. Now, if I combine all the W1, W2, W3, you'll see once they are multiplied with beta, it becomes
Okay,
different, right? So yeah, makes sense. Definitely. Hidden layers, right? The exact same example. So let's say I try to predict a price with this equation, the simple equation at the top. Right? Carpet area into 100 plus floor into 10 plus 10 into bedrooms. Right? So in this case, let's say you have a 600 square foot area and you have 3 BHK. Right? Now in isolation, 600 square foot is okay, right? So we'll have a certain price associated with it. In isolation, 3 BHK is great. So we'll have that additional price associated with it. But that combination is very bad for you. The moment you get a 3 BHK 600 square foot flat, you won't buy. So naturally, its price would go down. Right? So this equation doesn't account for that combination effect. It just says higher the bedrooms, increases the price, higher the carpet area, increases the price. But there could always be a combination where let's say I make all possible combinations: 500 square feet 1 BHK, 501 square feet 1 BHK, 502 square feet 2 BHK, and so on. Right? Number of neurons would increase, number of net new features would increase. Yes. Great question. So how would you form them, right? Using neural net, I will come to that. Are you comfortable with dummy variables? Probably not, right? Dummy variables? No, I'll come to that. No worries, no worries. I think the problem that you're having figuring out is the combination is just too many, right? That's the problem. Yeah, I'll address that. There is a mechanism. I don't want to go into a lot of technicality of it. It involves creating dummy variables, which will ensure you don't really have to create those many combinations. The one that I talked about, right? 500, 1 BHK, 500, 1, all that. Exactly. Each of the this neuron or this circle is a different feature. So you could have as many neurons as you want. You'll have those many new features. Exactly. You make a decision. So instead of using the root features, you use this combined interacted features. Cool. So just to summarize, a hidden layer is just a framework for the features to interact with each other. Right? And we've seen an example why that's important. That's all that a hidden layer allows. Now, do we only need one hidden layer? No, we can have as many hidden layers as we want. In the second hidden layer, the features of the first hidden layer will again interact to create new features. So first hidden layer is interaction of root features. Second hidden layer is interaction of root features. The third hidden layer will be interaction of root features, and so on. Right, so more the hidden layers, more complicated interactions are you basically creating. Cool. We good so far? Perfect. Yeah, go on.
Really, I think we can make maybe better decisions if there are more hidden layers. So what is lost if you have more layers?
Great question, right? So just two areas to look out for. The more complicated features you create, the more you tend to overfit. So if I have to explain overfit, have you heard the term before?
Yeah. So it doesn't generalize well to unknown data.
Exactly. Right. So you need to only go far to sorry, go on. Yeah, to an extent that it doesn't overfit. Right. With every additional layer that you're creating, you're basically creating more complicated features which might try to memorize the data rather than learn from it. Right? That's something you do not want. Perfect. So one open question. Let's say we have 3 features, right? Technically, how many neurons can I have without making the structure redundant? So when I say redundant, adding one more neuron will not capture anything new. Almost there.
Okay, plus bias. So 9?
In the reverse direction. Oh, sorry, I'll quickly repeat the question, right? You're on a great track. Just keep thinking. Till in the meantime, I'll repeat the question. See, what we have seen so far, what is a hidden layer? It's a framework for the root features to interact with each other and create new features, right? Let's say I have 3 features, and let's say I create 200 neurons. After that, let's say if I add one more neuron, it's not doing anything new. It's already doing something that one of the neurons already did. Right? So what is that number k, which is the theoretical maximum limit for n features, beyond which it doesn't make sense to add one more neuron? Great point. Great point. The only limitation with that is every combination, right? You'll only see one weight of it actually impacting y. When I say let's say 3f plus 4f, 3f1 plus 4f to that impacts y, then some other combination of the weights will not impact y because it's redundant. So it's a linear combination of the original, right? So the moment it's a linear combination, it doesn't make sense to add one more feature because you just change the beta associated with that combined feature and create the new feature. Because it's a constant that you're adding, right? Either dividing or adding or multiplying, right? So moment you identify one weight of combination or one combination of weights for 2 features or multiple features, exploring multiple combinations will not make sense because it's again a constant transformation from that original feature. Okay. I know I'm not probably completely explained that. I'll explain, but right now just assume one combination of weights is one feature interaction. Right. So sorry, coming back to you. Yeah. Eh,
And again,
Great answer. How did you come to that?
so okay, so if
I'll come to you just after him. Yeah, go on.
so if you have three features,
Huh?
then you can probably the most interactions you could model between
Hmm.
those three features would be okay between 1 and 2, 1 and 3, 2 and 3, 1 and 1 and 3 is already done. So
Right.
by so n into n minus 1 by 2 in handshakes basically would be your interactions,
Hmm.
right? So anything more than that would be redundant because what other data point do you pick from?
Perfectly put, right? That's the answer. That comes to 2 raised to n minus 1. But
Huh,
your
n into
concept
n
is right.
minus 1 by 2.
Right. Because let's say you have 3 features. By the way, I think that was also your thought process behind 7, right? Because that's 2 raised to 3 minus 1. So 3 features, you can pick them 2 at a time, 3 at a time, 1 at a time. That's it, right? So that's 2C1 plus 2C2. Sorry, 3C1 plus 3C2 plus 3C3. That's 2 raised to 3 minus 1. Right. So if you understand what it does, you'll get this. So if you have n features, think of all possible way they could interact. You could take 1 at a time. You could take any 2 at a time, any 3 at a time, any 4 at a time, and all n at a time. Right. You generally do not take as many neurons because it's computationally again too expensive. But theoretically, that can be the maximum limit. I did a couple of interviews when we only had 4 features, and the candidate ended up making 500 neurons, which doesn't make sense, right? If there are 4 features, the maximum interactions that you can have is 2 raised to 4 minus 1, which is 15. Right, so just keep that in mind. Great. So if you're good so far, I think we can actually start discussing on activations. It's all 11:30. I'll pick up speed. Right. So now we have seen what the hidden layer is, nothing but combination, right? On top of that, we apply some transformation just to address the problem of non-linearity that we discussed. Right. This transformation and neural networks is one of the 4 that Kavi discussed. You either have sigmoid, you have tanh, you have relu, not even softmax. Softmax is only for the last layer. You only have 3, right? And this is where we thought that the existing neural network architecture is slightly inefficient. If you look here, right, the transformation is being applied on the combination, right? And that's where the problem occurs. Most of the real life example that we did see, different features. Let me go back to those examples, right? Different features had different ideal transformations when it came to explaining why, right? Productivity needed sigmoid, marketing spends needed log, valuation needed exponential, and so on, right? So whenever you have a tabular data, it's very difficult for all the input features to have only one transformation that could probably explain why. And that's sort of what activations functions try to do. Because the transformation is on top of combination, each feature doesn't get to choose its most appropriate transformation. Let's say F1 wanted to choose log, F2 wanted to choose exponential, F3 wanted to choose sigmoid. It's not able to do that in the way neural network uses activation functions, because the activation is applied on top of the neurons or on top of the combination. Is that part clear? Unfortunately, in neural network, for all the neurons in one layer, you can only apply one transformation. So for one layer, you can only choose one transformation. And that's another problem why each feature will not be able to choose its own activation. Right? Perfect. So this is what we are proposing. As Kavi mentioned, it's still a research area. We only tried it out in a couple of projects, so you won't find this online. So I just wanted to also take all of your views, right? This is what we're proposing. What we'll do is, instead of applying the transformation at a neuron, we have created a bouquet of 15 different transformations. Sorry. Yeah, perfect. So what you're proposing is, instead of applying the activation transformation on a neuron, we have chosen a bouquet of 15 different transformations which will apply on the root features. Then use Pearson's correlation coefficient to identify the best transformation for each feature, and only that best transformation goes ahead. Right? So for something like a valuation, only the exponential would go ahead. For something like a vintage, only the sigmoid would go ahead. For something like a marketing spend, only the logarithmic transformation would go ahead. That's a great point, right? This probably is more relevant for regression use case where outcome is continuous and not a classification. And we'll also spend some time on why is that we are saying that. Yeah, go on. It's not discrete. It's continuous. Yeah, unbounded. Infinite possibilities. Yeah. Yeah, we have a coding example with a real life data. In fact, let me talk about example writer because there's a question, right? Let's think of the age of a building impacting the house price. More the age, the lesser the price, but it won't always keep decreasing, right? You won't see the house price going negative because it's 200 years old. It again caps at a certain point, and the decrease is again saturating, so it's more of a log. Right? You'll have different features where you'll see exponential relationship as well. Carpet area is linear because that will keep on increasing with a constant beta. Right? So we have a real life data set. We'll go through this with the actual impact and accuracy as well. Right. So before we open the notebook, this is one PayPal project that we did try out. We had 73 features, out of which only 7 did not require any transformation. Again, the same concept that we discussed, right? Most relationships in real life are non-linear. They need some transformation before we can actually use them. Right? So 15 needed sigmoid, 7 needed inverse, 39 needed exponential, 5 needed either square root or square, and only 7 were kept as it is, right? 7 features were the linear transformation was the best transformation. You also see the improvement in accuracy. The R square went up from 94.2 to 96.1 because of these feature activations. So not only did it make it explainable, it also ended up making it more accurate. Right, which makes sense. If a feature is not best transformed before it goes into the neural network, naturally it won't be explained the why, not be able to explain the why that well. Right, and we could sort of see. Yeah.
How well the variance is being covered by the model. Greater the number, better. So it means the model performance has improved post applying transformations on features at a very high level. Yeah.
The graph that you're talking about, right, is loss function, right? A convex loss function. Yeah. Yeah, I think you're probably confusing with loss function. Loss function or convex? Yeah. No. Yeah. So what you're talking about is a loss function. Loss function is nothing but how an algorithm decides how good is the fit. Right. For us, we get to see the error. For algorithm, it's the loss. Right. So root mean square error is a loss function. It's convex, but yeah, it doesn't necessarily have anything to do with the activation functions because activation functions are unbounded and they have all kinds of shapes. Exponential will have a very different shape compared to sigmoid, compared to log. Right, so they don't necessarily have a U-shaped curve. They don't. No. Some are bounded. For example, sigmoid is bounded between 0 to 1. It's just the way the transformation works. If you look at the formula of sigmoid, right, no matter whatever the input is, the output can only be between 0 to 1 because it's 1 upon 1 plus e raised to minus x. So most of how the transformation works. Any questions so far? If you're good, we can probably look at a quick code example. We good? Good? Perfect. So let's quickly look at a coding example. Yeah, please go on.
I'm just trying to draw an analogy here. Whatever you have done with this activation functions, is it somewhat similar to what ensemble learning has done to general models in ML? So for example, would it be similar to what bagging is doing, taking multiple models and then averaging them? So would this be similar to that in some sense?
Probably not. So what bagging does, right? Let's say you have 100 features. It doesn't use all 100 at a time, right? You split your data into multiple subsets, build multiple models, and then combine it. Right. So in this case, there isn't a split as such. We're just trying to explain each feature in its most appropriate form, to put it that way.
Okay. Got it.
Code, right? Definitely we'll walk through this. Yeah. Yeah, we'll go through each of the line. No worries. Perfect. So let's start the code walkthrough. Some of the statements are not relevant. I'll delete this. Zoom in a bit. Yeah. Oh, sorry.
Visualization, for example, for learning Python, there is a Python tutor where we can see what the code is doing. Like this.
Right.
Is there any visualization? You want to see how the neural network what is happening backside, like how can we visualize
There could be, but not in this code. No, we haven't.
for like
We haven't had.
use for Python, like
Mhm. There could be, but yeah, we don't have that in this code.
okay.
We'll try and explain it as much as we can.
Okay, thank you.
No worries. We can share the GitHub link and the data. Do you guys have a laptop in case you want to code along? You do? Perfect. Both. Actually, it's not in GitHub. I can share the code, right? Can you share?
Scholar to make it public so that anyone with the link can access and paste the
You can do that. Do you want to? Or you can probably share the email IDs.
This is taken, right?
Kavi, hello. So just for my understanding, right, I'm just clarifying my thought here. So what you're doing is like again feature engineering, right? You're trying to transform the data into relevant another feature and then trying to give that as an input.
That's right. Yeah.
I just want to reiterate the idea here, right? So if we consider example with one node, so let us say there are 3 inputs for that one single node. Now we understood that all 3 inputs for that node will be multiplied with individual weights, and an activation function is applied on that entire sum, not individual features. So activation function is not applied separately for feature 1, feature 2 or feature 3. It happens for that entire sum. Now our idea is to apply transformation on individual features before we even move it to the activation function. By transformation, that is what Romil explained, different features might require different transformation. Once we do that, before even move it to the activation function part, the features that you pass would be transformed. Now this makes a huge difference in terms of model performance. That's the core idea.
Okay. So the slide you said you choose the transformation function based on the Pearson coefficient, but the code doesn't reflect that. So that is something that.
Which one?
Yeah, we'll walk to the code.
Okay.
So this block's clear, right? You're just importing some libraries. Okay, sure. OS just helps me get some features such as the path. If I want to specify or extract my current directory path, all of that is a part of OS. That's it. Operating system.
If you are working on this notebook in a local directory, right? You want to quickly fetch a file from a particular path. Now, how would you access this path in your system? OS actually enables you to get that path. So, for instance, if you do a os.getcwd function, it gets you the current directory's path. Basically, we use OS to fetch that CSV file. Nothing more.
We have sklearn and TensorFlow's required libraries for neural network. Yeah, it's one of the most rudimentary model building frameworks. TensorFlow is slightly more advanced and more recent. This is just getting the path. This is reading the CSV, a basic head, right? The data. I have to import it again. Let me import. Anyways, let me walk through the code. So in the data, we have only 4 features: vintage, floor, area, and percentage sold. Vintage is nothing but the age of the building. Floor is the number of floors. Area is the carpet area. Not much of is done. Great. So yeah, this is data looks like. Just 4 features. Percentage sold tells you what's the percentage of properties sold in that building. Area is the carpet area. Floor is the number of floors. Vintage is the age of the building. Price is your target variable. Now the reason these values look very weird to you is we have scaled the data before giving it to you, just to make sure your pre-processing effort is saved. Now scaling is a very basic pre-processing. What we basically do is, instead of letting the values run haywire, we restrict them into a certain min-max range. Right? That helps the computational speed. It just helps the gradient descent to go to global minima faster. Right? So these are all actual values where you had an area of 500, where you had the floor 27. These are just transformed to fit into a range, a very small range, so that the computational efficiency is faster. Right? Nothing else. These are actually actual values, real data transformed to look small. That's it. So you're going to predict price using these 4 features. Let me quickly run this for you. This is my basic. Oh, perfect. Yeah. Okay, perfect. So if actually we are at 12, right? So let me do this. Let me not explain the neural network right now. If you have time, we can come back to this. For now, just assume that if you run this code, a basic neural network is built. Is that okay? Perfect. Great. Thanks. Right. So if you build a basic neural network, look at how the loss varies. It starts from 0.72, and in the last iteration, the loss goes up to 0.42. Right? Again, naturally lower the loss better. So with a basic neural network without transformation, this was the best loss that you could have had. After that, what we did is we applied all possible transformation to all features, which was exactly the question, right? We did not choose. We just applied all possible transformation to all features. And we built a neural network on top of it, exact same code. You will see the loss going down to 10 raised to -4, in fact, -5. Right? So the huge drop in loss, a huge gain in accuracy with the exact same features just by transforming them. There was a very relevant question asked, which was, we did not choose the best feature yet. Right now, all we have done is we have used all possible transformation, given it to neural networks. That's what we wanted to do as a part of this exercise. Unfortunately, we won't have the time, but please do it. Right? A simple code, use the Pearson's correlation coefficient to identify the best transformation, and just run the same code again. See if that helps. But what we did prove that even if we do not choose the best transformation, if we just blindly put all the transformation, the gain in accuracy is still huge. Right? We went from 0.42 to 10 raised to -5, kind of a loss. Yeah, go on. Just the root features. Just these 4 features. In fact, if I show you the for loop, this is how it looks like. So my features has that 4 features: vintage, area, floor, and what was that? Percentage sold. Thanks. Right. And each of the features goes through these 5 transformation: log, square, square root, exponential, sigmoid.
Okay.
Inverse. We haven't chosen the best transformation yet.
Okay. Now you come up with a like which feature is performing well with which transformation.
Ideally, yes. Yeah, ideally we should have done that. But what we have done so far is just given all transformations to the neural network to make a model on top of it.
Okay, like
To figure out the minimum loss.
28, right? So we have 4 into 7, 28 features now. 4 features, each transformed 7 times. So as root feature, we have the log of it, we have the square of it, we have the square root of it, we have the exponent of it, we have sigmoid, we have inverse. Yeah, please. Yeah, that's exactly what the code does. It will start with random weights and it will use gradient descent to reach to most optimum weights.
So you mean for the different transformations, 5 transformations?
Exactly.
Okay.
Yeah. So what you should see, right? If you print the neural network, only the best transformation should have a weight, let me go back to that.
Okay, this seems very intuitive kind of thing. Something has not been done before,
Exactly. So that was our surprise as well. How is this not being thought of before, right?
Right.
Because it's very difficult for all features to have a one transformation,
Yes.
and everywhere you see this activation force fitting it on top of it.
Right. Yeah.
We did do our research. Nothing of this sort has been done before.
Nice. You can write a paper.
Sorry?
You can write a paper, I'm saying.
Oh, definitely. That's on the that's in the pipeline for sure. Any other questions? You. Hidden layer, we still have a lot of neurons. What you're actually doing is, instead of starting at the features, we are starting at transformed features. Trade-off which we try to navigate through this use case, right? So it's possible that a feature might have a different transformation in isolation and a different best transformation in combination, right? In case you do what we had initially suggested, the best transformation in combination might be lost, right? So that's the reason in this programming use case, we did not choose the best transformation. We just gave all the transformations, and that definitely worked. That again would be a problem if there are a lot of features.
But again, if you are going to have the maximum number of neurons, right? Like for in this scenario, for 3 inputs, if you are going to have 2 power 3 minus 1 neurons, and apply this transformation on all that combinations, yeah, you could probably overcome that. But again, there are a lot of transformations, right? If you were to try and test out everything, and in real world you work with a lot of features, not just handful of 20, maybe even hundreds of features. Now if you were to apply, like let us say there are 500 features and there are like at least 10 transformations, you end up with 5000 variables. Now having a neural network built using these 500 features with multiple hidden layers could actually lead to a lot of computation.
So would you say this is ready for implementation in the real world, or is it still more of a work in progress?
If you've done it in our projects, which again has a lot of data, so we do have 1 billion cards, thankfully at PayPal, right? But that's it. That's the extent of it, right? We haven't published it anywhere else. In fact, this is the first public forum that we're talking about this. So yeah, we just have a couple of very large projects and one house price prediction, small data.
Right. Yeah. Thanks.
Yeah, we are actually trying out all the possible combinations, right? And from that only we are taking the best suitable one by applying correlation coefficient and all those things. So like we already have all the different combinations. So like how are we missing it out? Like
I'll explain that. So what we are doing is, let's say you have housing price as your Y, right? Let's say you have vintage or age as your X. You'll use all possible transformations, then choose a transformation of age which best explains your price. So far so good. But it's possible that maybe a log of age explained price well in isolation, but an exponential of age might explain price in combination with some other feature.
so in that for loop we are doing it for
For
the
all
combination.
features. In that for loop, right? This for loop, we are applying transformation for all features
Right.
and all transformations.
Yeah. So
this way we do not miss out on anything.
yeah, that's what I'm
But
asking.
yeah, this way we don't. But if we choose the best transformation after this, we might miss out on some other optimal transformation in combination.
Okay.
So in this code, yeah, we are missing out on nothing, but then it's computationally little bit time consuming, right? It might not really work with a very large data.
The best transformer must be the one that is best on the combination of features, right?
That's right.
Yeah, so after all the permutations, after all the hidden layers are crossed, whichever combination we find whichever transformer we find the best on that feature shall be used, right?
Rightly put. So best transformation on the feature, but used in combination, yes.
Yeah, so also isn't a single transformer used for all features a good option if we consider what would be optimum for the combination of all features?
Only if a single transformer explains all features, yes. But that doesn't happen.
No, but after you permute them or you multiply them, they will have a certain value which will. So I don't think the scalability here will matter because we use different transformers.
Okay.
So what I'm trying to say is, if we use a single transformer, for example, say standard scalar, for all the features. After going through all the hidden layers, it will have to be multiplied with all the other features and everything. After doing all the combinations, it could be the optimum, because it won't matter if we it will be the best. It has to be the best if we apply a single transformer. Is it not that
So
case?
let's take this example again, right? Let's say price is equal to same. Thanks. Carpet area into 100 plus age into 10. So in this case, ideally what you should have done is taken a log of age for the very same reason, right? As age increases, yes, price decreases, but it won't go negative after some point. It will saturate. So in this case, carpet area has a linear relationship, age has a logarithmic relationship. Now, how will you fit both of them into one transformer? That's a problem. So we'll have to transform this first and then combine them in all possible form that we can. But the transformation has to happen before that.
Also, after training the model, is there a way to find which transformers would be best suited for each feature?
Definitely. Great question. Great point. What you can do, right? You can print each neural network along with all the weights. So what actually happens is you will see the weights associated with a bad transformation very close to 0. That will automatically tell you that those transformations are not impacting Y at all. And if they're not impacting Y, naturally they're not required.
So essentially, you will have to code for all the transformers you could apply.
You just have to transform and give it to a neural network. It will automatically interact. So you just have to...
Yeah, but you'll have to find the loss for each transformer individually.
The loss is always combined.
Which combination works well? Like, is there a code like best params we have in hyperparameter tuning? Is there a way to find it directly after we have trained the model?
So unfortunately, feature importance doesn't work for neural networks. You won't get a feature importance graph. So one way to get around that would be to print all these weights. So if you look at these slides, right, each neuron has 3 weights, one coming from F1, one coming from F2, one coming from F3. Right? After you transform, F1 will be age, F2 will be log of age, F3 will be exponent of age, and so on. So if you just look at these weights, the weights which are very close to 0 naturally are not good transformations. So that would be one way to understand after the model is built what transformation worked and what did not.
Okay.
Right? But feature importance, yeah, it doesn't. Neural network doesn't give those feature importance like XGBoost does.
Okay.
So that wouldn't work. I'll add that code. Yeah. You anyways. Exactly. You have the link. I'll add that code which will help you extract the weights.
Okay. Yeah. Thank you.
Any other question? Yeah. Okay.
Are we only considering that newly transformed features for our model, or do we consider the original ones also?
Originals also, because the linear feature can also impact Y.
Okay, that's totally makes sense.
Highlighted in one of the slides, right, the last one, where 6 of the features, if I'm not wrong, didn't require any transformation.
So in this case, we can consider this a feature transformation as a feature engineering. Like we are creating extra features.
Could be. Generally, feature engineering requires creating non-redundant features. So technically, it's not feature engineering.
Okay. Did you able to get a chance to see the correlation between the original features and the transformed features? How it looks?
This would be that this table. Are you talking about this?
Okay.
Which transform?
Correlation between the transformed feature and the original feature.
That would always be 1, right? Because as the original feature increases, the transform feature will also increase. Because it's basically redundant. The transform feature is made from the...
If you find the correlation, it's going to be 1. Because it's the same value, you just have transformed it. That is not going to change the relation.
Right. So this would be that table. We don't have all the values, but this tells you the best transformation which worked with compared to the output. So out of 73, 7 features were such which were sort of best explained in the original form only. None of the other transformations made them better. 5 features required square or square root and so on.
Activation function usually
that it's meant to capture the non-linearity present in the data, right? So
Right.
how are these transformations also? Do these transformations also achieve the same objective, or is it something else that we're trying to do?
Exactly, Protect. So activation functions were supposed to do that. Just that with structured data, they don't. Right? Because they apply on the combination of features, not on root features. They don't tend to capture the non-linearity data. It works very well with unstructured data. That's where they have been also applied, right? Most of these architectures became famous on computer vision or NLP. Then it makes a lot of sense because of two things. In unstructured data, a feature in isolation doesn't make any sense. Let's take an image of a pixel, right? A brown pixel could be my t-shirt, could be my retina, could be a bench. You only know what that is if you combine that with the with the neighboring pixels, right? Same goes about a text. A letter R could probably mean any word. You only know what it is if you combine them with the neighboring letters, right? So in those unstructured data use cases, you need to combine first and transform later. That's the reason activation functions become very famous and very relevant in unstructured data, because you have to combine first, transform later.
That is when they capture the non-linearity.
Yeah, they were able to capture non-linearity in unstructured data because the combination was required in unstructured data first. But in structured data, it's not necessary. Age could be besides income. Right? Age could have a very different relationship. Income could have a very different relationship. So transformation needs to happen before, and then you need to combine. Right. Perfect. Any more questions?
Like, if we are on to try to make something like this, like some machine learning algorithm, some machine learning algorithms for predicting something, or like as mentioned like this, how is the training process actually? Like, how do we train this particular code? Like, how is it done while you are designing an algorithm? Like, you set up a code as shown, and you have a set of data that is available to you. And how do we train, or like what is the process of training? Like, how do we get the correct result after a lot of data is being fed? Initially, a lot of data is being fed, and by that methodology is being understood by that algorithm. And when a new person comes and given an output, it gives an actual correct output. That is what it's doing. It is predicting. So what is the training procedure for getting this accurate results actually? Like, if we want to try and implement or make a model for ourselves, what all are the procedures that we can try out, or what all are the things that we should follow for the same?
Matching with the number of features, right? Those guidelines they are interested.
It's a very long answer, to be honest, but I'll try to make it as short as possible. Let's start with choosing an algorithm first. Right? Let's take a first bite. It's first about getting the data, right? You have to identify what is your Y, what are your X's, what's your output that you want to predict, and what are the influences that you're going to use to predict. Right? The influences become your X's, the output becomes your Y. Now, once you have the data, the second step would be to choose an algorithm. It could be neural network, it could be XGBoost, it could be regression. Right? Because we discussed neural networks, let's only focus on neural networks, right? Let's say we go ahead and choose a neural network. Then it will be about choosing an architecture. How many hidden layers would you want? How many neurons would you want within each hidden layer? What would be the activation function? Unfortunately, all of this currently is based on experimentation. There's no thumb rule as to these many hidden layers would work better in this case, or these many neurons would work better in this case, or this activation would fit the best. We try everything possible and then choose something that works the best. Right? So all of the work around designing the architecture of neural network is still based on experimentation. You start with the most simplistic model first. Let's say only one hidden layer with only 10 neurons. You keep adding complexity till the point it doesn't overfit. Yeah. After a point it will overfit, that's when you stop.
So after a point, like this code understands what we require, is it?
Yeah, the reason code is very small, there's a lot of complicated code at the back end of it that we're just calling packages, which is doing a lot of complicated stuff. That's the reason the code looks as if just 4 lines, but it understands and it does all of what we discussed.
Here we are trying to modulate the features into something that would make the accuracy go higher. How would it compare if we are just decreasing the step sizes and increasing the epochs in response to that? Like here we are transforming the features because the weights are not able to tune to a finer granule and are not able to explore more possibilities. So let's say if the feature lies in the logarithmic scales or something like that, the weight is not we have limited epochs and a certain step size which is restricting the feature to not explore in that domain. So would it how would it battle against if we just reduce the step size and increase the number of epochs?
Great question. In fact, when we started this, we had this discussion, right? Are we sort of leading to faster convergence, or also are we doing something that couldn't be done before, couldn't be done without this, right? And the answer to both were yes. It also leads to faster convergence. You need lesser number of epochs, you need lesser iterations, but it also improves the accuracy in the sense, even if you did reach the global minima with all the epochs that you could do, you wouldn't reach the accuracy that you can with the transform features. The only reason being, no amount of weights tuning will compensate for not finding the right transformation.
Yeah, okay.
Right. But yeah, that's an excellent question. We did ponder upon that for some time as well. Perfect. I think we did extend by almost 20 minutes. Thanks. We also did start late, but still. Thanks for being so engaged throughout, right? If there are any questions. Perfect. That's all. Great.